I wanted to start off class just by kind of framing the last few days in a more global context. So I think a lot of you voted. I think if you voted, hopefully you submitted your picture of you voting to the Canvas assignment, and I'll give you guys credit on the next exam there. One of the there's a lot of big outcomes of this exam. This election. Question or comment?
This is for CHEM107.
Did they print out CHEM107 twice?
Yeah. Oxidation number of C and methane.
Let's do that. Let's do that.
This is the first time they've ever done that. They literally printed out the same thing for my 107 and my 108 class. So we'll be working off of other notes today, so don't worry about worksheets.
Okay.
So one of the biggest outcomes long term of this election could be this. There's a lot of talk about jobs, about a lot of how people are treated and all that kind of stuff, but this one I think is particularly scary, and I think it's something worth talking about in this class. What does EPA stand for? What is that name, that acronym? Protection, right? Protection is a big part of that word. This administration sees it differently. So they're putting someone in charge of protecting the environment who thinks that climate change is a hoax and that humans don't have anything to do with it. It's pretty messed up, right? There's a lot of other things along these lines that are going to be happening. And the reason I'm bringing this up is not to get into politics or talk about that, but you guys are going to see the impacts of these next 4 years and any changes that happen, and you guys are the ones that are going to be able to do something about it. So over the next couple of weeks, Ms. Terrell and I are going to put together some studio activities that kind of get us thinking about climate change and our role and some other things. What's that?
How we can be actively involved.
Yeah, so how we can actually play a role. Instead of sitting back and being pissed off about it or saying that sucks, I do want you guys thinking about what you can do in the future in order to play a role. Climate change is not just like something that's like, oh, we'll put it off for later, it's like smog, right? Smog, you'll get sick for a little while. Climate change means that we literally change the face of the earth. Like right now, Miami. In Miami, at high tide, they have pumps that run throughout the city to pump water out of the storm drains because the sea level rises up that much. Even just an inch that the sea level has risen means in Miami they're going to be underwater, right? It's going to happen, it's a matter of time, no matter when that happens. So like the fact that we're going to ignore it, turn our back on it, and increase the rate of production of CO2, Trump wants to move towards a coal economy again. Like there's a lot of really concerning things, and so I want to make all of us aware of what's going to happen and what our role can be. So not to go off too much on the political side, but one of my take-homes from this class is that you guys will understand how we play a role in changing the climate of this planet and what we can do in order to try to combat that. Does anyone else have any comments they want to add? Concerns?
I hope that we can do a really positive spin on it too, and not just like, oh, that really sucks. Yeah, it does kind of suck, but we're doing some really awesome things with what we have.
Yeah, and for me this is a time of action more than a time of, I'm not quite sure how to take all the protests that people are doing. I like the idea that people are voicing their concerns, but I'd rather think about what we can do rather than just voicing concerns, actually thinking about actions. So hopefully that's something that we can generate some ideas together on.
Doesn't the legislative branch thought to approve it?
So Cosme's question was, doesn't the legislative branch, isn't there checks and balances, basically, right? Yes, to a certain extent, but the Keystone Pipeline, that's something that can be put back on, and right now the House and the Senate are both controlled by Republicans, and there's a lot of people that are persuaded by financial interests in order to push that through. So the fact that we had a president that did block, like literally he had to block it, right? It was going to go through. That is now no longer the case. Even if there was a Republican at all, that's one part of it, right? But then changing who the EPA, the director of the EPA is, I don't think that has to go through Congress, as far as I understand it. Val?
I don't know if this was already talked about, but why are they skeptical of climate change?
It takes away from our economy because it means we're not able to use cheap coal, so we lose jobs. instead of thinking about how we shift the jobs to something else, like trying to get renewable energy production as a source. So one thing is lobbying, right, by coal and other people. So if you look at the background of the person who's being put in that position, he has a lot of money coming from lobby groups that are interested in clean coal, or whatever the hell you want to call it. The other thing is, well, how much do we influence it? And people can argue that this is a cyclic nature that's been seen throughout history. You guys know better than that. You've actually seen the NASA data, and you know that's not true. Pauline, you want to add to it?
I don't know. I had to follow this stock for another class. And it's like a agricultural machinery stock, and it went up because with like Trump being the next president, he's like pro the drilling and like more coal mining, and so that's like looking more
Pro fracking, pro drilling.
Yeah, so like their stock went up because then they would improve. And it also said that he wanted to cancel the Paris Climate Pact.
Yep, and so that's one of the first things on the chopping block is the Paris Climate Agreement, which means that we are actually going to try to decrease our carbon footprint in the world. Instead, we're going to just get rid of that so we don't have that regulation. And so now companies can do whatever they want.
Isn't there no, like, and isn't there nothing binding a country to actually doing anything? There's no, like, specific thing that they have to do if they're part of that treaty.
So there's,
Like,
from what I understand, there's no negative impacts per se directly stated in that treaty saying something negative has happened and you withdraw from it.
Yeah, there's no punishments.
There's no punishment, but there can be trade agreements that go into play with the communities or the countries that are in agreement with the Paris Agreement. If we withdraw from climate change, England and other European countries would decrease their trade in certain perspectives as kind of negative impact to say, no, you should be pressured into joining us in this.
why would it benefit us to withdraw from that?
Because I think the big picture, it's probably because we don't want to be held to a standard that someone else agreed to, is what might be perceived. So it's more of a gentleman's agreement than anything, I agree. There's probably some smaller impacts.
One really positive thing that I do want to input about that, and I'm sorry, I'm like going off on so many pages, but in terms of the Paris Agreement, one really positive thing is that a lot of companies are already finding it more economically positive to go in a more environmentally friendly route. We consumers are choosing the energy and consumption that we want to see. We want to see cleaner energy. We want to see cleaner production, things like that. We can reward those companies that do use cleaner energy and cleaner production so that those companies will individually by themselves decrease their carbon footprint.
Yeah, I think saying that the market's going to drive itself towards the destruction of the planet is excessive. But I think that there are a lot of companies that put profit way before the environment, and having an agreement or laws in place that limit the amount of output that companies can do is something that I think the future administration will get rid of. So they're basically leaving it up to, if you feel like you should help the environment, go for it. Okay, so on those positive notes, we're going to be thinking about what we need to be doing in the future and what we can do. So, building off of what we've been doing in studio the last couple of days, today we're going to be working with equilibrium and talking about buffers. In order to do that, we really need to talk about the strength of conjugate acids and conjugate bases. I really wish that you guys had the correct worksheet because there's a lot of stuff that you guys will be kind of working on today, but I think that overall you guys will be doing a right job with it. If you have the worksheet from last class, why don't you pull that out because there's actually a decent amount from that. And so the first points we're going to be doing is we're going to be working with Ka and Kb. Do you have access to the file? We're going to be looking at conjugate acid base pairs like you guys did in workshop this past week, and we're also going to be talking about buffers. We're going to see how Ka and Kb relate for a conjugate acid base pair through Kw. And we're going to use that all to do some more conversions between pH, concentration of OH minus, concentration of H plus, And we're also going to be doing some ice tables as well. Since there's a lot of really good activities, POGIL activities for equilibrium, we're not going to get through all of them. So here's some really good study tools for our next exam. Our next exam is December 2nd. It's Friday after you come back from Thanksgiving. These activities I think will be really beneficial. In the past I've had it the Monday that students get back. That people didn't like that very much. POGIL activity number 43. Did you guys start on that in workshop last week? So finishing the rest of that would be beneficial. POGIL activity number 45 just helps for converting back and forth between concentration of H+, concentration of OH- and pH and POH. Activity 46, it really gets into the molecular reasons for why certain bonds are weaker and hence more acidic than other ones. So I really recommend working on these. And then I've had Smart Work updated with some end of chapter problems from these chapters that we're working on now. So there's some questions on equilibrium, on weak acids and bases. So this is the question that you guys had at the, what was our next question at the end of the worksheet from last class? I want you guys to estimate what the Ka value would be for benzoic acid. And I'm going to see why this thing is not starting up. You have the OwnCloud link. So let me, OwnCloud. If you just go through your email for OwnCloud, you should be able to see the link to that folder. So talk to your neighbor, see if you guys agree. What would you guess the Ka of benzoic acid to be? And why? You guys are 50-50 split. Toss your neighbor. Try to figure this out. What are you guys thinking? Why? You sure about that?
I'm not sure.
Okay. So it sounds like one you need to memorize. Strong acids. Okay, it's not a strong acid. So what else tells us it's a strong acid by looking at it? That it is not. What about looking at that formula that tells us it's not a strong acid? All right, let's see where you guys are at. Not really sure. We're leaning towards the Ka of less than 1. Why? Pat, what would you say about this? What would you guess the Ka to be and why?
I think that it was less than 1 just because benzoic acid is a strong acid, so it wouldn't totally be acidic.
Okay, so first of all, we can say not a strong acid. If you have not yet memorized your 6, there's only 6. Come on, guys. If you haven't memorized your strong acids, do that. That'll let you look at this immediately and say, well, it's not a strong acid. So therefore, the Ka has to be less than 1. What's another way we can look at this if we didn't have our strong acids memorized and know that that is not a strong acid? What about that formula tells us that's not a strong acid?
The benzene ring.
So the benzene ring is there, but that's not necessarily what tells us it's not a strong acid. Well, so there's NH, and I've highlighted that H is probably acidic, but how do we look at that and know that that's not a strong acid?
Never mind. Is it an OH?
So let's draw 2 structures here. So benzoic acid, and this is benzoic alcohol. What can we tell by looking at the structures of those 2 compounds? Are both of those very similar compounds? No. Why? What's so different about these 2? These 2 would act completely differently in water. One would dissolve, one would not.
Is it because one has a polar group and the other one doesn't?
So both of them have polar groups, right? OH is polar.
Carbonyl group.
So it's not just about the carbonyl, but this functional group is absolutely different from this one. The one at the bottom is an alcohol. If you guys don't know your functional groups, that is something else you have to learn. And the reason we have to learn our functional groups is because the function, anytime we see a carboxylic acid, this is a weak acid. This OH is extremely differently from this, acts extremely differently from the OH on the bottom. Those are not the same. OH does not equal OH. Right? Because if OH equals OH, then lithium hydroxide would also be an acid because the O and the H would separate, right? Is lithium hydroxide an acid? What is it? It's a strong base. It's the opposite, right? So let's not get stuck in a routine of just seeing OH and thinking it's an acid. Why? So why is that top structure so different from the bottom structure? Why is it that top one is an acid and the bottom one is not? Talk amongst your group. Try to decide how you can predict that the top one would release a proton and the bottom one would not.
There's more resonance structures. You got rid of the hydrogen, there's more resonance structures.
Right. So what does that mean that OH so much less?
You only have one resonance structure, you only have 2 or 3. Pretty much.
There's no this drawing up there.
You have more resonance structures than carboxylic. That's all I remember.
It's easier for it to give a hydrogen because the ring, it already has a lot of stability in the ring. They do. But that OH, like, it's already okay where it is, you know what I'm saying? But when there's that carbonyl group on there, it probably has to
Why? Because I named it. I named it wrong. I named it.
sure that
All right, so what ideas do we have? Why is that top structure likely to give away a proton, and that bottom one would almost never give away that proton? Cosme?
If the carboxylic acid lost the hydrogen, it would have more radical structure.
So if we lose, let me try to clean this up a little bit. If we lose a proton from the carboxylic acid, so let's do an equilibrium arrow here. We would have a carboxylate ion. And that has 2 resonance structures. You can move that negative charge there and push it back there. Which of those 2 resonance structures is right? Which one is more accurate? What do you think, Alex?
The resonance structures have like a combination of both. That's how it exists.
I'd flip it the other way around maybe, but so that the actual structure is an average of the 2 resonances.
Yeah.
Right? So the resonance shows us 2 different parts. So how much of a negative charge is held at each one of those oxygens? Like half, right? It's an average of having 1 negative charge and having 0, so that means it's actually a half of a negative charge. When we try to find the best Lewis structure, what do we focus on in our drawing? Once we assign all the electrons appropriately, how do we check to make sure that's a good Lewis structure? We decrease the formal charges. We try to find the one that's most stable, right? The most stable is the one with the least overall formal charges. So that has half of a negative charge. What if we did the same thing? What if we removed the proton from the alcohol? How much of a negative charge would we have on oxygen, Demetrius? If we tried to say this, that we're going to remove that proton. Yeah, how much of a negative charge is there on this oxygen?
Would it be 2 now, so you just remove another proton? Or would it be
Well, careful, there's only one proton, so when we remove it, there's a full -1. There's nowhere for that O- to resonate. There's no way to decrease that negative charge. So the more resonance structures we have, the lower the formal charges at each one of those individual sites, which means the more stable it is. You will never see an alcohol giving up a proton unless we forcibly remove it with an incredibly strong base, which you'll see if you took organic chemistry, or when you take organic chemistry. You can make that happen, but it is not by any means what's called an acidic proton. So just to give you a heads up, in my class, if you show an alcohol acting as an acid, I will destroy whatever you did on that problem. That is one of my biggest pet peeves, is just looking at OH and assuming that that's an acidic proton, because it's not. Just going forward, that's a warning. That's one of my biggest pet peeves in this class. So, let's draw one more structure. Is this a weak or a strong acid? Or is it an acid at all? And why? Talk to your neighbor. Try to decide if the structure I drew in purple would likely be an acid. Would it be a strong acid? Would it be a weak acid? Why?
There's an electron on the top.
All right, so raise your hand if you think the compound in the bottom left corner is a strong acid, or it's likely to be strong. Okay, why are you guys saying it might be strong? Don? Okay, so this is HClO4, perchloric acid. It's on the list of strong acids. Why else would that likely be a very strong acid? Michelle?
Because if you remove the proton, then the charge can disperse between 4 of the oxygens.
We have 4 resonance structures. That 1- charge is distributed equally amongst 4 oxygen atoms. That means that each oxygen really only has about a quarter of a negative charge. That's pretty stable. What about the compound in the top right? Do we think that might be an acid too? What do you think, McKenna? Mia, what are your thoughts?
Would be a weak acid because it still makes resonance structures.
So if we were to remove that proton, if we were to donate that proton, we would have an O-, and it could resonate between 3 oxygens. So let's say this. So I'll say both of them are acids. Talk amongst your group and decide which of those 2 structures, HClO4 or HClO3, which one of those is a stronger acid and why? Okay, so which one do you guys think? Dana, which one do you think is a stronger acid and why?
Yeah, you're right. I was going to say this one.
Cosme, can you bring it back together? Claudia? Thanks. Dana, can you share your thoughts?
Not really sure. I would guess is going for HCl.
Why? Okay, that's true. It can make the most resonance structure. So then does that tell us it's a stronger acid? Thomas?
I think that the lower left one is because in resonance it's gonna have a smaller.
Okay, so each oxygen is going to have about minus a quarter of a negative charge. And in the top right, it's going to have a negative a third. So it's a larger charge per oxygen. So what does that tell us? Why does that tell us that that's a stronger acid? What does an acid do? What does a base do? Shane?
It's more stable and it releases the proton.
It's all about stability. If something is stable when it releases an H+, it's more likely to stay that way. If it stays that way, it means the H+ is floating around, well, with water, but that it generates more H+ in solution. That alcohol, if that is really unstable being apart, what does that tell you about the compound I have circled in purple on the right? Is that an acid or a base? It's a base because it really wants a proton. It really, really, really wants a proton. So that I would consider a strong base. It's not one of these strong OH minus bases, right? Hydroxide bases. But if we were able to make that benzoate, then that would definitely be a strong base. That would snatch up any proton it would find, and it wouldn't stop until it consumed everything. So the reason I'm digging into this so much is because buffers are all about how likely something is to release a proton and be stable, dictates how likely it is to accept that proton back and to become what it started out as. It's that conjugate acid-base pair that we really need to be thinking about. So, we want to be talking about, for benzoic acid, that we can write out, for any carboxylic, any acid at all, we can write out the expression of it interacting with water. What's the equilibrium constant that we use to describe how a weak acid interacts with water? Brian, what's the equilibrium constant we use to describe how a weak acid interacts with water? Those are useless. So we have a weak acid interacting with water, forms a conjugate base and acid on the far side. What's the equilibrium constant, guys? Kc, but we're more specific because we're talking about an acid, so we're going to hone in on the change. So this is Ka. So we're going to describe this equilibrium with any weak acid as Ka. So then what is Ka? Go ahead and write down what Ka is for this reaction. All right. So what's Ka? Let me hear from Kirk. What's your Ka expression for this?
K equals the concentration of C6H5CO minus times the concentration of H3O plus the concentration of benzoic acid.
Great. So you don't have concentration of water in there. Did you have another question?
Yeah, that's why my hand is actually.
Is it something you want to ask now, or you want to wait until we're working on the next problem?
I can wait.
Okay. Pauline?
So why don't you include, when do you and when do you not include water?
You include water when it's a reactant and you're doing Kc. If you're honing in on just what the change is for an acid, then we're going to wrap up the concentration of water in Kc, and we're going to call that Ka. Okay, so the generic version of this reaction that we're always going to be using is we have a proton attached to some conjugate base. When those go in water, they're going to separate out. We're going to end up with our H plus and whatever that conjugate base is, or the anion A minus. And so there's a generic version of Ka that you're always going to see. Concentration of H plus times concentration of A minus all over the concentration of HA. So we've been talking about weak acids, and we're also going to talk about strong acids, right? So strong acids are strong electrolytes. Strong electrolytes, sodium chloride, other salts that dissociate 100%. You guys remember back to semester 1, do these things actually separate 100%? No, why not? Why do these salts and strong electrolytes not always separate 100%? Don?
Because the solution gets super saturated, it just can't dissolve anymore.
It can be saturated, but even before they're saturated, we usually say that it's more like 95% or greater. Why is that?
Isn't it because of how the NaCl forms like a crystal or something like that?
Well, so if we dissolve it, we'll still find every once in a while about 5% of the sodiums and the chlorides together instead of apart. And that number changes based on how attracted those two counterions are to each other. So really it's about how stable are they apart, how stable are they together, and if they're in water and they're solvated, it doesn't always end up being 100%. So with the 6 strong acids that we have, we assume 95% or greater dissociation or separation between those ions. So our strong acids, that means if we ever see HCl, we're going to put it in water. There's no equilibrium arrow there. We say it's 100%. It's going to make only H3O plus and Cl minus. And that full-sided arrow, the whole arrow that only goes to products, that tells us that that reaction goes to completion or very, very close to completion. So then, what's the conjugate base of HCl? Cl minus is the conjugate base. How strong of a base do you think Cl minus is? Talk amongst your group. How strong of a base is Cl minus? So let me hear your thoughts, Jose. How strong of a base is Cl minus?
I would say, yeah, I guess it's strong.
Okay, so give me some more than that. Give me some more than I guess. Why?
I would say maybe some
So let's take a step back. What does it mean to have a strong base? What does a strong base do? Kira, what does a strong base do? Okay, so if we had an equilibrium arrow, so let's go back to benzoic acid. C5 or C6H5CO2H plus water goes to C6H5CO2 minus plus H3O plus, right? So the acid is the one that releases the proton and goes to the right. Is everyone cool with that? So then what does the base do? It goes in the opposite direction, right? So this is the base, or sorry, I'm saying that backwards. This is the acid. This is what the base does. How do we know that it goes in both directions? There's an equilibrium arrow, right? Okay, so let's go back to HCl. Same rationale. How strong of a base is Cl minus? Why is everyone in this room wrong? Why is it a terribly shitty base? It's not an equilibrium. Right? To be a base, it has to want to go in the reverse direction. That Cl minus has to want to grab an H plus. Does it? Is there any attraction at all between a Cl minus and an H plus? That's about as bad of a base as we can imagine. It's something that has no affinity for H plus. Not only does it not want to interact and steal a proton from water, which is our definition of a base, but it doesn't even want one from H3O plus.
Why doesn't it want a proton?
because it's stable as it is. So we showed some other ones that have resonance structures, and that's why they're stable, right? And chloride is actually one. The group 7s, the halogens, they're stable for the most part, with the exception of fluorine, with a full octet without any binding partner. Is that what you're going to ask me, Michelle?
Yeah, I just because with the minus, like keeping charging things that I would want an H plus.
Yeah, so if we had O2 minus, right, that wouldn't be very stable. But the further we get towards the noble gases, that halogen group typically can hold on to negative charge and be stable. So 2 ways. One, it's close to noble gas configuration, only needs 1 electron, and it's relatively stable. It has a large atomic radius. But the other thing is, we need to pair that with our memorized list of strong acids and rationalize it both directions. If we know it's a strong acid, we know that that should be stable, and hence we should be able to look at that and say that if that's stable, then it has no basic properties whatsoever.
If strong bases, aside from, okay, here's the list of strong bases. If something's strong bases is a strong base because it'll fully ionize. If I have a bunch of chlorine.
What do you mean?
It'll completely ionize, like NaCl will break up into NaFCl.
Does that mean it's a strong base or a strong acid?
Base.
No, neither. So we have to look at something. In order to define whether it's a strong acid or a strong base, we have to say, does this have any likelihood to accept a proton? Is it a strong propensity to accept a proton? If it's really unstable without a proton, it's considered a strong base. If it has the ability to release a proton, and it's very likely to release a proton, then it's considered a strong acid. But it's only about the proton. It's not about whether it ionizes. So there's a category of strong electrolytes. That's anything that dissolves in water that generates a cation and anion. Right? So sodium chloride, those are all strong electrolytes. All the salts that dissociate 100% are close to it. But if that dissociation leads to the generation of an H+, that's a strong acid. Does that make sense? So that's a smaller category within strong electrolytes.
So are all strong electrolytes bases, but not all bases are strong electrolytes?
Strong electrolytes are not always anything. Strong electrolyte just tells you they separate. That's it. End of story. Then we have to look at what they separate into. So to play into your examples, I can give you 2 examples right off the bat. HCl dissociates into H3O+ and Cl-. Strong acid, right? Strong electrolyte. Lithium hydroxide, what does that dissociate into when it goes into water? Lithium plus and OH-, strong base. So being a strong electrolyte just tells you that there's nearly 100% dissociation, and then we have to look at what is there, and if the thing that's there accepts a proton, it's a base. If it donated a proton, it's an acid. So I really want to step out of the strong electrolyte tells you anything about it until we know what the products are, and then we can start saying. So that's the case for nitric acid. That's the case for perchloric acid, sulfuric acid, at least the first proton for sulfuric acid. Once we've removed the first proton and we have hydrogen sulfate, that second proton is a little less stable to pull off. But all of these we can predict based on the stability of what we're forming when it goes into water. There's another term that you guys might run into, especially if you do careers in medicine, and that's this term of normality. So normality is the number of protons that you get when something dissolves in water. So if you have a 1 molar solution of HCl, you have a 1 normal acidic solution. What on this list might not have a 1-to-1 ratio between molarity and normality? Sulfuric acid. We can consider that if both of these protons were to be released from sulfuric acid, that a 1 molar sulfuric acid solution would be a 2 normal acidic solution. So it's just a little bit of terminology that you might run into. All right, so let's look at these 2. Which type of acid is the anion, or the conjugate base, more strongly attracted to a proton? Which one of these 2 would you choose? Talk to your neighbor to try to work through this.
There's a strong acid, weak base, so we have.
All right, everyone clicked in? So Salma, can you explain your thinking process? So it's all about whether that reaction is going to 100%. The top one, nitric acid, that is only that nitric acid is going to release a proton, and then that nitrate, that polyatomic ion that we form, it has no strength to pull a proton back, and hence there's no reverse arrow. Javante?
Could you ask the question in different words? I don't really understand you.
So the question is, once we generate the conjugate base, right, once we release the proton, which one of those conjugate bases has any basic strength? So does that help a little bit? Or so can you explain it then in your own words why B would be the better answer?
Because it would be more stable with the proton than having NO3 minus because it would have more resonance structure,
Right, so NO3 minus is more stable than benzoate, the conjugate base in the bottom. So I don't want to say that nitric acid, well, we can say that for these two, because we know it's a strong acid. We know that nitrate is stable in water by itself. For the second one, I don't want to say that one side or the other is more stable. We need to look at the Ka to decide whether it's more stable as products or reactants. But we know that there's both in the mixture when it's stable. Does that make sense? It's not only about products, which it is for a strong acid. So this is where we're getting into this definition of the stronger the acid is, what do we say about the strength of the conjugate base? The stronger that acid is the conjugate base weaker or stronger? It's absolutely weaker. Who has heard something else when they've been in chemistry class before? Strong acid makes a strong base or some crap like that. There's some misconceptions running around, and it has to do with the relative strength of an acid and a base. So what we're going to be doing is we're going to be talking about how we define the strength of that base. What's a nice way to describe the strength of a base? How do we describe the strength of an acid, besides strong or weak? How do we numerically describe how strong an acid is? Ka. pH is what we find depending on how much we have there, the concentration. pH is not a definition of how strong the acid is. We can have a really weak acid, but if we have a lot of it, we get a low pH. So then how do we define the strength of a base? Let's do Kb. All right? Here's a little thing that you guys need to be really, really careful about. Is this the reverse of Ka? Brianna, what's different about this than the reverse of Ka? Anyone figure out what the difference is? Okay, Kirk, you want to be more specific, maybe?
Well, in the reaction, you have the C6H5CO minus and H2O instead of benzoic acid and H2O. And then in the products, you're getting benzoic acid taking a hydrogen from H2O, leaving you with OH.
Cosme?
Water's the acid in this one.
Great. So if we're defining Kb, that is saying if we were to take this base and put it into water, it's not the flipped of Ka, it's water specifically. Water, if you're around here. So it's a base plus water. How likely is this to pull one of the protons off of water?
This reminded me of home.
It's my wife. She comes out every once in a while when I start talking. All right. So when we say how strong is an acid, how likely is an acid to donate a proton to water? If we're talking about how strong a base is, how likely is that base to steal a proton from water. It's all about the relative ability to donate or pull a proton from water, okay? It's not just the flip of the reaction. So then I want you guys to go ahead and write Kb for this reaction, for that conjugate base. Write on your page somewhere what the reverse reaction is, or the Kb reaction is. Does anyone need scratch paper? Is anyone running out of space on their notes? Ms. Terrell, can you maybe grab a couple people? Or does anyone have extra paper they could donate? Michelle has some. Raise your hand if you would like to borrow a piece of. Oh, you have some as well? Does anyone who would like a piece of scratch paper? Alright, if you need one, ask Kira or Michelle. Thanks, guys. Sorry about the printout mistake today. Probably my fault.
You gotta write KB. Oh no. Can you tell me if I'm right first?
Nope. So just write the line, write the expression. Alright. Thank you, Alex. So, oops. And I just... What just happened? What just happened? Undo, undo, undo. Son of a... Ah! I don't know how I just did that, but somehow I erased everything that was on there. So what Alex had written, and I'll do it really quickly again, was Kb equals concentration of our, let me just do benzoate with an H on there, concentration of that times concentration of OH minus, all over the concentration of benzoate with a negative charge times the concentration of water. Does everybody agree? What's that? I agree. Everybody else agree? What can we do to focus a little bit more on what's changing, though?
Take out water.
So this is Kc, not Kb. What we've written now is Kc. So if we want, so I could go ahead and erase this. That's Kc. But I want Kb. I want to focus on what's changing. So what's the difference? No water. Concentration of my conjugate base times the concentration. Oh, sorry.
But why even though because water is aqueous, so why not?
So one way that we can write this out is to say that we have our weak conjugate acid times the concentration of conjugate acid times concentration of OH minus divided by the concentration of our weak base. Concentration of products over reactants, that's Kb. This, once again, focuses on the change that's occurring. There's so much water around. Has anyone ever calculated the concentration of water in an aqueous solution? Any idea how concentrated water is? No, it's not. It's a molarity, right? It's how many moles there are in every liter.
Oh.
We could calculate that out. A liter of water is 1,000 milliliters. We could figure out how many moles there are in every liter. Comes out to about 55 molar. Water is 55 molar. So in the course of a reaction, with a little bit of base pulling a proton off, it's not going to change. So we're just going to put that as a constant in Kc. All right, so that's Kb. That's how we write it out. And the really important part of it is Kb describes how likely are we to pull a proton off of water. Not from H3O+. It's not the reverse reaction that we have for Ka. So let's look at Ka and Kb. McKenna, too fast? Do you want to write? I'm gonna keep moving. Okay, so let's look at a generic acid. We're going to use HA as our generic acid. H means that there's a proton attached to something that's likely to release. You all right, Tatiana? And then A is whatever the anion is. And the last one is benzoate. It can be Cl- if it's a strong acid. It might be chloride. Whatever it is, that A-, that's the conjugate base. And so we describe Ka, concentration of products over concentration of reactants without water in the equation. And then we say, well, how strong is the base? That's when we put that same conjugate base into water. How likely is it to pull a proton from water? And then we have Kb. So the question is, how do these relate to each other? Justin? So it's all about water. Water is the focal point for both of these. And if we're talking about the same HA and A-, what would happen if we multiply Ka times Kb? On your own paper, write out Ka times Kb and see what you get. So write out everything that Ka equals times everything that Kb equals and see what you get left over. All right, take about 10 or 15 more seconds to try to write it out.
You get water.
All right. Alex, can you share with us, once we get Megan to calm down a little bit? Alex, what do we get when we multiply Ka times Kb?
The concentration of H3O plus times the concentration of OH-.
Have you guys seen that before? Ka times Kb is the concentration of H3O plus times the concentration of OH-. That's not water necessarily, but it has to do with water. Does anyone remember where we've seen this before? Have we seen this before? Maybe we haven't seen this before? Kw? What is Kw? It's a dissociation constant of water. So what does that mean? What happens? Why does water have a dissociation constant? Water's stable, right? What happens? Why do we have this dissociation constant for water? Cosme?
Because it's an acid and a base.
We've seen water act as an acid. We've seen water act as a base. And it turns out it doesn't have to be around an acid or base to do that. That every once in a while, two water molecules come together, and one of them steals a proton from the other. And for a small fraction of time, we end up generating H3O plus and OH-. So let's take a look at this. If we were to go on the magic school bus and zoom way in and see a couple water molecules, every once in a while, we would catch this happening. We would catch two water molecules, and one would steal the proton from the other. Not very stable, right? So that means that most of the time it's going to go back. But that we have, at any point in time in water, we have a mixture of both of those. So if we look at a whole solution of water, that every once in a while we have very, very small amounts of this happening. And yeah, this is kind of dizzying, right? It's a really small amount of it happening. But if this holds true, basically what we're saying is that if you have two water molecules, that there's an equilibrium constant that describes That's Kw. You guys see what we're doing there? Concentration of products over concentration of reactants. But once again, it's not Kc. This is an equilibrium constant. We're focusing on what's changing. And what's changing is the concentration of H plus and OH minus. So Kw is describing that ionization. It's called auto-ionization because it happens regardless of what else is around. And here's where everything gets tied together. How do we find pH if we have POH? If I gave you guys a POH, how do you find pH? Subtract it from 4. Where does that come from? Where's this number 14? Why is it so magical? Comes from Kw. So Kw tells us that in a neutral solution of water, we have an equal concentration of H plus and OH minus. And if you notice, I'm using interchangeably H plus and H3O plus. We have an equal concentration at a neutral solution. What's the pH? If we have a pH of 7, that's neutral. If we have a pH of 7, what's our POH? 7. That means we have the same concentration of OH minus as the concentration of H3O plus. Does everyone see where those two are equal? Which means, what is our Kw?
1 times 10 to the negative 14.
How'd you get 1 times 10 to the negative 14? What's that? So if we're neutral, that means that the concentration of H3O plus is the concentration of OH minus, which is 1 times 10 to the negative 7. So that means that we have 1 times 10 to the negative 7 times 1 times 10 to the negative 7 is 1 times 10 to the negative 14. So what's pKw? Dan, what's pKw? Yep, so what is that? What's negative log of 1 times 10 to the negative 14? I'll give you a hint. It's a really easy number that you've heard a lot. What's that? 14. So pKa plus pKb, what does that equal? On your pieces of paper, I want you to write down Kw equals Ka times Kb. Everyone got that? I want you to write out that Kw equals 1 times 10 to the negative 14. Hence, pKa equals 14. So then what is pKa What does pKa plus pKb mean? What is that? What is that value? So we have the 2 things up there. Yeah. We have the 3 things right there. So with everything below this line, you should be able to answer what pKa plus pKb is. And I'm going to give you a hint. You don't need a calculator for it. So Val, what does pKa plus pKb equal? Equals 14, which is pKw. So what does that mean? Okay, we have a lot of numbers, and we're laying them all through this number 14. What does that mean? If let's look at a strong acid, all right? We can look at Ka and Kb for a conjugate acid-base pair. If we have a really strong acid, what is the Ka value going to be? What's Ka for a strong acid? Greater than 1, right? It's going to favor products. So what is Kb going to be? How do we find Kb if we know Ka? Careful, you're doing P's now. So let me clear this screen off. Let me give me some whiteboard. So for a strong acid, Ka is, let's say, 1 times 10 to the 8th. Let's say that's our Ka for a strong acid. How do we find Kb? So we do Kw divided by Ka equals Kb. So 1 times 10 to the negative 14th divided by 1 times 10 to the 8th is our Kb. Is that a big number or a small number? Stupid small, right? 1 times 10 to the negative 22nd. Okay, work with our exponents here. Let's take a guess. What would Kb for Kb? What is Kb for something that would be a strong base? Would Kb be large or small for a strong base? Just the same as Ka. If we have a large Ka, it's a strong acid. If we have a large Kb, it's a strong base. So is this Kb tell us that the conjugate base of a strong acid is weak or strong? It's so weak, it's like off the scale. It doesn't even exist. 10 to the negative 20. That means that there's 21 zeros to the left of whatever that Kb is. It's a really, really small number. So I want you guys thinking that the stronger the acid is, that we can calculate proportionally the weaker the conjugate base is. We can have some, maybe we have a weak acid with a Ka of 10 to the negative 7. But it's equally as good of a base as it is an acid. And then as one gets the properties of it, becomes a stronger acid, it'll become a weaker conjugate base. Or if it's a stronger conjugate base, it'll be a weaker acid. So when we're looking at this conjugate acid-base pairs, we always want to say we're looking at how water interacts with these, and we're defining our whole scale around water. This is really not an incredibly useful slide because we've already talked through this. So, trying to remember what I was doing with this. Okay, so as Ka goes up, what happens to the strength of the acid? If we're comparing two acids, one has a larger K than the other, what can we say about the strength of that acid, Jose? Higher Ka means a stronger acid. So then the pKa is always a bit confusing, right? So let's look at this table right here, and I want you guys to click in the pKa of the weakest acid in this table. The clicker questions up on the screen. I want you to look at that table of acids. Click in the pKa of the weakest acid and think about what the trend is. All right, a couple more seconds. All right, as last before finishing clicking in, Ms. Thurl and I thought it would be useful to bring in a visual to kind of think about this. We thought magnets might be a nice example, right? So a lot of people kind of get this mixed up. If you have a stronger acid, how much attraction is there between the H plus and the conjugate base? If we have a strong acid, how much attraction is there between? So the stronger the acid is, the less the attraction is. Which means it's easier to pull them apart. And when they come back together, you have to get them really close together and they'll finally be attracted to each other. On the other hand, if you have a weak acid, that means that to pull them apart in the first place takes a lot of effort, And that means that when they get closer together, that there's a lot more attractive force that pulls them back together. So you can say like the strength of a magnet, right? That the weaker the magnet is, the stronger the acid would be. Which means that the desire to pull the things back together is not really there. But the more attraction there is between that H plus and whatever else is there, the less likely it is to stay apart, meaning it's a weaker acid, meaning that that base is more likely to want to steal that proton back. So if we're looking here at these numbers, then the one here that is the weakest acid is the one that spends the most time together. Why could I have done that without looking at the pKa's? Or how did you guys answer that? Alex, how did you answer this? Okay. The only one without an acid in the name is phenol. All right? Cool. How else? Justin? Yeah, there's 9 zeros before that. So, or you could say it's 1 over 10 billion is this fraction here, right? There's 1 in the dissociated state for every 10 billion that are together. What's one other way we could have looked at these formulas and determined which one is the weakest out of all of these? What did we say earlier? What functional group is a terrible, terrible acid? OH with no CO next to it. C double bond to O. Okay? This is an alcohol. Phenol, the OL at the end of the name also tells us an alcohol, and that's a terrible, terrible acid. Okay? So basically we're saying that as pKa gets bigger, that our strength of our acid decreases. Right? Negative log means it kind of flips it around the opposite way that you think. So then let's answer this another way. Ask this another way. I want you to look at this table of acids, and I want you to type in the number, the orange number next to them. Which one of these has the strongest attraction between a proton and the conjugate base when they do separate? You can scoot over and get closer. There's 6 screens in the room. I think you guys can get close enough to them. Which one is less stable? One. Okay, so that means it spends the least amount of time apart. Because what?
Because it's
Kind of a circular logic question. All right, everyone clicked in? Must decide. All right, closing out. So Tatiana, do you mind explaining your rationale for which one you chose and why?
So, the higher the Ka value, the stronger the acid. So, you find the lowest Ka value, you find the weakest acid, and the weaker the acid, the stronger the attraction between the proton and base.
Incredibly well said. I agree with you. The only reason people might have chosen 8 is because you're not so good at your numbers. What's bigger, 4 or 1? 4 is bigger than 1, so 1 is smaller. So 1 times 10 to the negative 10th is smaller than 4 times 10 to the negative 10. All right, so pay a little attention on those guys. But I really like how Tatiana said that. She used the description of the stability of the conjugate base. The less stable the conjugate base is, the more likely it is to spend the time together. Will it spend time apart? It will, right? 1 in every 10 billion times you look at one of those molecules in water, it'll be apart. Considering that we have moles and moles and moles of stuff, well, that's still a lot of them that are separate. But relative to the other ones, there's 1 million more hydrofluoric acids that are separate compared to the phenols. We can also say the same thing about any base. So, what's that? What's that, Kirk? Yeah, I don't know.
I'm just confused as to why there's a picture of Invader Zim on your PowerPoint slide.
Because Dr. Fajardo's son likes it, and we developed these slides together last spring.
I approve.
All right, so which one of, so if we write out KB for any basic, by the way, why do I know that NH3 is a base? Okay, because we've written it out that it accepts a proton, but how do I know that NH3 can be a base? We know what our strong bases, right? Our strong bases are anything that has a group 1 metal and a hydroxide. Or if we took an alcohol and removed the proton, that's a pretty strong base. So then why do I know that NH3 is a base? It's a weak base. Why? Alex? Okay, so our equation tells us that it is, but why do we know off the bat that it's going to be?
Can't nitrogen break the octet rule? So it's like already stable as NH3, it's still able to extra protons.
So careful, it can't exceed the octet rule, but it has a lone pair of electrons. And so it can choose, if it has an H plus around it, or steal one from water, it can choose to share those electrons with the H plus. We'll give it a positive charge, because it still has that octet, but now it isn't in possession of as many of the electrons. So any nitrogen with a lone pair of electrons, or I hope you guys are seeing a trend that anytime you have a carboxylate, carboxylic acid that has a negative charge instead of that H plus, that is also a base, a weak base. So these are two things we're going to recognize as weak bases. In the last couple minutes of class, I think actually what I'm going to do is I'm going to talk about the connection back to lab. Okay, so we've looked a lot at having an acid-base, a conjugate acid-base pair. So if we have a weak acid, we put it in water, and let's say that we have a Ka of okay, we're going to use, let's use 5 times 10 to the negative 6th. What pH would we have to have in order to have an equal mixture of the conjugate acid-base pair? Talk amongst your group. Try to figure out how to answer that question. At what pH do we have a 50-50 mixture of the weak acid and conjugate base? What are you guys thinking? Think back to what you did in studio. All right, so who has a good idea? How do we know exactly at what pH we have an equal mixture of the weak acid and its conjugate base? Did anyone find a number? What did you find, Don? Nope. pH of 7 is when we have an equal mixture of H plus and OH minus from only water with nothing else in it. So we could find KB through that. What equation have we seen where we have a mixture of the weak acid and its conjugate base? Henderson-Hasselbalch. So the pH equals the pKa plus log of the conjugate base over the concentration of the weak acid. At what point do we have an equal mixture of both of those? What would the pH be? So let's, instead of doing concentration of those two, we'll do same number on the top and the bottom, right? 50, whatever. It doesn't matter what number we use. They're the same. What is that? Log of 1? Did anyone find the pKa? What you guys are doing in your lab is you're experimentally playing around with this, that when we're looking at a graph of a titration, which is what we're taking our weak acid, we're forcing some of it to that side, or we're taking some of the conjugate base, and we're adding an H plus and moving it to the left side. And we really need to focus in. The thing I want you guys to focus on the most in lab on Monday or Tuesday is that it's one conjugate acid base pair. If we add a proton, we move from A minus to HA. Granted, it's diprotic. Or if we added a base, it would take it from HA to A minus. No matter what happens to the ratio between those two, that the concentration of H3O plus, that will change in order for Ka to remain the same. So numerically, let's always keep an eye on Ka is constant. So that means that if one of them something goes up in that equation, something else has to go down. And H plus is the thing that changes in those reactions, which is our pH. All right, so keep that in mind. We'll get back into this in detail next Tuesday and begin working on buffers. Have a good weekend, guys.